So good morning. I am Krishna Kumar. Welcome to Krishna's Classroom. We continue with our lectures on analysis on R. What we looked at last time was the gradient of a function. In fact, we had a function f defined from E contained in Rn to R, a real valued function. Then we defined a vector valued function grad f the matrix representation of grad f is represented by, see, grad f is at x defined by d1 f sorry, it is e1 e2 en, that is what we have used. It's a vector field defined in E. Okay. Then we proved certain results on this, and in fact we proved that if proved that if U is a vector, if U is a vector, then we defined the directional derivative along U not equal to 0 by of f u1, or it is essentially this is equal to grad f dot u. So this is where we stopped last time. So in short, what happens is that this grad f carries all the information about the variation of the function along all directions at the point x. This is one of the outcomes of this. And let us just recall something also. Note that divergence of if f is sufficiently smooth, then this is equal to what is called the Laplacian. Okay, this is called the Laplacian of now the solutions of the Laplace equation have an important role to play in the potential theory, and in fact in electromagnetic theory as well as in fluid dynamics this plays a very important role. And the equation, sorry, this delta, or I'm sorry, this notation is delta. This is equal to it's in the potential theory, it has an important role to play. In the theory of, in the electromagnetic theory as well as in fluid dynamics, this Laplacian plays a important role. So these are all some of the things, this came essentially from physics. So we shall not discuss this at this stage, but maybe on some occasion we will have a more detailed discussion on this. Now, what are the things that we would like to do is the following. Recall that if you have a real valued function from an interval a, b, r, say differentiable, on AB, then the mean value theorem that is say if x1 say, then we have f of f derivative at psi into where psi is some point open interval. This is the mean value. It talks about the existence of a point lying between x1 and x2 such that this property holds. Okay. Now geometrically this simply means the following, that if you have take R2 and suppose this is x1, this is x2, and suppose the graph of the function is something like this. Now you see that if you take a, okay, this is the fx2 minus fx1 is divided by x1 minus x2 or divided by x2 minus x1 is the slope of this line. So what it says is that there is some point lying between x1 and x2 where the tangent to the curve is parallel to this line. And it's quite clear that what it says is doesn't even say which point it is going to happen, but it simply says that there is some such point. And in fact it is also true that there could be several points having this property. So this height is fx1, this is fx2. So if you take fx2 minus fx1 divided by x2 minus x1, then this is the slope of this chord, okay, joining the point x1 fx1, x2 fx2. And this, what this theorem says is that there is some intermediate point where the slope of the tangent to the curve is the same as fx2 minus fx1 divided by x2 minus x1. Okay, so this is the mean value theorem. Now we will try to work out something of this point, something of this type in the case of vector valued functions. So let us work on that. Okay, so the next theorem is dealing with this problem. So we are having, suppose E is a convex subset of convex open set let f be a map from E to Rm. Assume f is differentiable in E and there is a number m such that norm of f derivative of x is bounded by Suppose this is true. Then what we have is f of b minus f of a is less than or equal to now this is the norm in this is the m norm, this is the n norm. Okay, so we are assuming the function is the derivative exists obviously, and by our assumption it's a differentiable function that we are taking up, and we assume that the derivative is bounded on, then this relation is valid. That is norm of fb minus fa is less than or equal to m times b minus a. Compare this with the mean value theorem, and here you see that, see, fx1 and if f derivative is bounded by m, then you get the same inequality. Okay, so let us see how we prove this. Now first of all, we are told that E is a convex set. Convex subset of R. The consequences that given 2 points, the entire line segment joining them lies in E. Okay, so let us prove this. Now, then the line segment joining A and B convex. We are assuming this. Okay. Now let us write down the parametric form of this line segment. Let gamma t be defined by Tb for t belonging to R such that gamma t belongs to. Now since E is convex, of course this belongs to this. Now we know that gamma t belongs to E for 0 less than or equal to t less than or equal to 1, because on this interval, now you see any arbitrary point on this is given by gamma t. Okay, for t belonging to, so when it takes t takes the value 0, then you get gamma 0 equal to a. In fact, gamma 0 equal to a and gamma 1 equal to. So let us now compose this with the, or in other words, see, you have E from here to R. Sorry, F is a map from here to R. Now we will look at the function that F sets up on this line. Okay, so let GT defined by f of gamma t. Or even beyond, I mean, there is no problem about that because we are assuming this is an open set, therefore this entire line lies on that, and some extension of this also would be lying on that, so there is no problem. So it's defined on a larger interval, in fact. Okay. Now let us compute g derivative. G derivative of t, we have already seen this. This is equal to f derivative at gamma t operating on in that order. Okay. Now if you see, what is this? What are these operators? See, f derivative is a map from Rn to Rn. So you have what about gamma t, gamma derivative of t? See, gamma is a map from the interval 0, 1 to this one. So gamma derivative belongs to Rn. Therefore, g derivative of t belongs to L Rn. Okay, so this is what you have about g derivative. We have elaborately looked at this in the last lecture. Just recall these things. Okay, let us now estimate this. Okay, therefore, what is g? G is a map from, g derivative is a map from R1 to Rn. So you have norm of, see, g derivative of t is in Rn. So you are working out norm of that. So you have norm of is less than or equal to with the appropriate norms used. Okay, for instance, see, g derivative of t is in Rm, therefore it is going to be m norm, and here you have what? F derivative of gamma t is going to be again f derivative is from Rn to Rm. Therefore, you are talking about the derivative of this. This is the operator norm, and this is also the operator No. So this is the operator norm for Rn to Rm. Now let me just make a mention of this. Suppose A is an operator from what is the norm of A? Norm of A is supremum of uh, 0, which is also equal to supremum of norm of x equal to 1 see this is m norm, this is m norm, this is n norm, and the supremum of this over the unit ball norm x n norm of x equal to 1 is what you call the norm of A. For a bounded operator, this is true. Okay. So you see that here what you have is that this is a norm of an operator. This is also a norm of an operator. So the appropriate definitions work for the norm. Okay. Right. So let us just keep it somewhere here for your reference. Now you see that this means that, so now you take g derivative and integrate it from 0 to 1, or I'll write it this way: g1 minus g0 now you see that g1 minus g0, okay, this is less than or equal to zero to 1, what is it? This is less than or equal to g derivative of t is, you are having a derivative into gamma derivative. So you have, this is less than or equal to yeah, let us work it out. What is this? This is equal to, see, this turns out to be b minus a. Therefore, this is bounded by, okay, so we have this part bounded by m. What is that? We have f derivative is bounded by m. Therefore, this is m into b minus a. That's a vector. Into d, which is equal to This is exactly what we put. Okay, but G1 is equal to, what is G1? How is G defined? F of gamma t. So this is equal to F of, and gamma 1 we have seen that is equal to B. This is equal to, sorry, this is F of B, and this is equal to F of gamma 0. Therefore, we have norm of now this is the result that we have. Okay, so we get that completes the proof. So let us now an important corollary. This corollary says that, again, just like the application of the mean value theorem, that if f derivative is 0, so you recall that on an interval, suppose f derivative is 0 everywhere on that interval, then f is a constant. So we are going to prove a similar analogous result. If in addition f derivative of x equal to 0, then f is a constant. Okay, so look at this result. Apply this result. So you see, suppose f derivative is 0, then you see that fb minus norm of fb minus fa for every a, b belonging to E, norm of fb minus which is a constant. So that completes it. Now what we want to look at is the smoothness of the derivative. That is, you know that suppose f is differentiable, then what we have seen is that the partial derivatives exist. Okay, that is one. So you ask the converse question. Suppose you know that the partial derivatives exist. Does it mean that the function is differentiable? Okay, so this converse question we asked, or does it require some additional further assumptions? Okay, so this is the question that we have asked. So to deal with this, before we look into this problem, we define what is called a C1 function. A differentiable mapping f e to Rn, where E is Rn, is said to be continuously differentiable in E if f derivative is a continuous mapping of so you have two spaces now. You have E and see, let us just write it up. We'll elaborate the whole idea. Now note that f derivative is a map from Rn. So you see that what, as I said earlier, what is the norm on L, Rn, Rm? So norm on is a normed linear space, and it is defined by the norm is defined by supremum of norm of x. Okay, so that's a norm. So you see that E is a part of Rn, it's an open subset of Rn, and you have the norm of Rn here, and here the norm of L, Rn, Rm. So L, Rn, Rm is a normed linear space with this norm that we have defined. Okay, so you see that you are having a map from one normed linear space into another normed linear space. Okay, so f derivative is a map from one normed linear space into another normed linear space. Okay. Now let us give the meaning for this. So the of continuous is the following. For every x belonging to E and epsilon positive, there exists a delta positive such that norm of f derivative of y is less than epsilon for y belonging to E and that is the usual definition that we have. Okay, so this is what you mean by the function or the of the function being continuously differentiable. Okay. Now we take up our question. Our question is what? Okay. Our question is the following. Suppose you have a differentiable function. Then we have seen that the partial derivatives exist. That we have proved. Okay. So you ask the converse question. Suppose you know that all the partial derivatives exist in E. Can you conclude that the f is differentiable? This is the question that you ask. Okay? Or is it valid only under some further conditions? This is the question. So let me pose the question and then we will take it up. Take up we also investigate a certain example and after that we give the main theorem. So what is our question? Our question is this. We know that if f is differentiable on E, then all the partial derivatives E exists. Is the converse true? This is the question then. That means, if you know that all the partial derivatives exist on E, can you conclude f is differentiable on E? Okay, that is f is differentiable okay. So let us investigate an example. Now we look at the following example. This is the one that we have looked at. Of course, f is defined from R2 to R and equal to 0 now. See, f is defined from, we have already investigated this, looked at this. Now, what one observes at the outset is that the partial derivatives of f exist at every point, including 0, 0. Okay? So, everywhere except exists and are continuous. That is because the function is there defined as x cubed divided by x square plus y square. Now you see that the denominator does not vanish at all. Both numerator and denominator are polynomials. Therefore, there is no problem about the differentiability with respect to x or y, and you know that everything is fine. Partial derivatives exist and are continuous. So this is the important point. Everywhere except at 0, 0. Even at 0, 0. So you can also show that this is what is called the function is differentiable. Zero. In fact, I think we have to wait until we prove the theorem. We prove a more general result. Okay. See, you can easily conclude this. Shortly. So wait until that. But we will examine the problem. Investigate what happens at 0, 0. So recall that the following. So we have d1 f, this we have computed already, f at 0, 0, this is equal to limit x tending to 0 of f of so the partial derivative with respect to x-axis at that point. There's no problem with that. Now let us compute this. Okay, so we will also look at this one, d2 f at 0. That is, this is equal to which is equal to which you know is 0. Therefore, both the partial derivatives exist at 0, 0. We have already seen that f is not differentiable. F is not differentiable. At 0, 0. So it clearly tells that the existence of the partial derivatives does not guarantee that the function is differentiable. Okay, what goes wrong? First of all, what you would observe is that both the partial derivatives df by dy, we shall observe that now you know that df by dx is again a map from E to R total. Okay. So what we prove is that you can easily see that everywhere except at 0, 0, the partial derivatives exist and are continuous. At 0, 0, the partial derivatives exist, but we will investigate whether it is continuous or not. Now you see that the following. Suppose f is differentiable then what we have is this: a equal to f derivative of 0, 0 with respect to standard basis this is given by, well, we know the partial derivative, so we can write it in terms of this. This we have already seen what we proved last time. Okay. Hence, let us look at this: x cube divided by minus the value of the function at 0, 0 minus 1, 0 working on xy. We will estimate this. Look at this, divided by norm of okay. Let us investigate this. What happens to this? This is essentially, now if you just recall, this is nothing but your f of xy minus f of 0, 0 minus a of the point h. Okay. Right? H is the increment. So we are taking this. We investigate this. Okay, this is the proof for that. Now you see that this is equal to which is equal to E by 2. And what you can say is, so along the direction y equal to x, okay, this is the direction. We see that limit which is this is the condition because we are fixing along this line. This is equal to mod or rather 2x square 3 by 2. And if you look at the limit of this, this is equal to 1 upon 2 to the power 3 by 2 and this is not equal to 0. Because we have already seen that if you were to take the derivative along the y axis, then it is 0, but this is not equal to 0. Whereas if you take the derivative along the y axis, that is along x equal to 0, 0. So hence we have that f is not differentiable. Zero. We also investigate one more thing, namely the behavior of the partial derivative. Okay. We also make the following observation. So in spite of the existence of the partial derivatives, now you see that this is not differentiable at 0, 0. Okay, because we have already seen that if the function is differentiable, then the partial derivatives agree. Okay, right? The partial derivatives exist. So let us look at the partial derivative. We not equal to 0, 0, and that's equal to whole 0. Now so you see that df by dx at 0, 0 is 1. That you see. Okay. Now you see that as so df by dx y tending to 0 or along the x-axis. This is equal to, you see that if you look at this expression, this is the line x equal to 0, therefore this is 0. This is equal to 0. Hence, this is not equal to 0. Similarly, df by dy, this is equal to whole square, and along x equal to y, df by dy is equal to this is equal to 2x to the power 4 divided by and this is equal to minus half. So now let x tend to 0. This is what we have seen as df by dy at 0. Therefore, df by dy is also not continuous. Make an observation. Although the partial derivatives exist. Okay. Now we are in a position to take up the main theorem. So we shall prove the following. Connecting the partial derivatives with the derivative. Suppose f maps an open set f belongs to C1 P if and only if the partial derivatives exist and are continuous on E for 1 less than or equal to I m 1 So if the partial derivatives exist and are continuous, then the function is a C1 function. Conversely, if the function f is a C1 function, then the partial derivatives exist at every point and are continuous. This is a sort of necessary and sufficient condition for the existence of a C1 derivative. Okay, let us prove this theorem. One part is simple. Prove the forward implication. Assume f is C1. Then we have the following: dj f5, this we have introduced the notation, this is equal to sigma connecting with the derivative dot u1. Okay, this is true for every I, j and x belonging to. Now we estimate this. Hence, ui. Now, since one, we have this is less than or equal to f by x. And this implies, of course, all those conditions that That is straightforward. It is just this relation connecting the, this is the crucial relationship that we need to solve. Okay. Now we prove the converse. The converse is the following. So we are assuming that all the partial derivatives exist and are continuous. Then we show that f exists, and that is f derivative exists and is continuous. Prove the converse. So this is one part, proving the converse. Observe that to prove it, m equal to 1. Now why it is so? Because you see our we have the function from E to Rn. Therefore, f has components f1 u1 plus un. These are all real valued functions. F5s are so if we can prove the result for each one of these fm's, then you can combine that and get the result. For example, this is what you want to do. Okay, this is so since. So suppose you compute this. What we want is f of x plus h This is the question that you are asking. Okay? This is the question that you are asking. As is it really true? Okay? So we show that if it is true for each one of these fi's, then it is true. Assume it is true for each one of these fi's. Then what do you get? You observe that, see, f of this can be written as sigma j okay, I equal to 1 to m ui. Okay, or let me write it here. y. So ah you can write as use this. Now you see that this is now use this, and then you see that if this is uh, if each of this goes to 0, then this is where AI is a map from then what you have is this norm of is less than or equal to and this of course you know it goes to 0, therefore this goes to 0. Okay. So that's our assumption. So if we can prove it for each fi, then we can conclude it for this. So we shall prove it for each f. Okay, let me show this. So we prove it for that. Okay. So fix belonging to and excellent positive. So since E is open, there exists an open ball with center at X and radius R. Now continuity of dj f shows that R can be chosen so that DJF at Y for Y belonging to S and 1 less than or equal to J less than or equal to K. This is possible. Now we work in a sort of systematic way. So this you know, okay, we shall use it. So now use a sort of step-by-step increment. Okay. So you see that suppose H equal to H anything. That is our conventional notation. H is the vector h1, h2, etc. Now define, so we set and Vk defined by Hk, K or 1 . So what it is, this is in the space, Vk is in the space spanned by or in other words, what you are doing is you are just taking the projection of H into this particular space, and that is what you are called Vk. Okay, therefore span of this is what it is. Okay, now let us work it out. Therefore we write this f of x plus h minus f of x, bring in some add and subtract certain terms. So this you can write as, this is the crucial step. So what happens is, you see, if you write out the terms, you will start with f of so I think we need from 0 to n. Right. Then we have Vj minus 1. Okay, right. So this is right. So if you write, this is actually f of x v1 minus f of x v0. v0 is 0, therefore this is f of x will come there. At the other end, when n is equal to j, you will get f of x plus h from the definition of vn is equal to h. From that you get this. And the intermediate terms will all cancel out. Okay. Therefore, since norm of Vk is less than R, the segment line segment joining x plus Vj that is because S is the ball that we are taking, therefore this is true. Okay. And we see that Vj equal to Vj. By definition, we can apply the mean value theorem. What does it give? It implies the jth summand is equal to some theta j. You see that this is a point that lies on this particular line segment for some theta j belonging to just the application of the mean value theorem. This is some intermediate point lying between these two values, these 2 points, that's x plus Vj and x plus Vj minus 1. Now we make use of the continuity of the partial derivatives. Okay, and you see that this differs Hj by less than norm of h into norm of hj. Therefore, we get the following. So these are the steps actually. So the crucial step is actually breaking up this into this. Then that is the step that enables you to write down the proof immediately. Let us write down this. Nearly through the proof of this. This is enough, we don't have to put that. Less than or equal to this epsilon, and which is less than or equal to this is norm of hj. Okay, norm of hj is h is equal to h1, h2, hn. Therefore, this is less. Epsilon. This is less than for every h belonging to therefore and that f derivative is the linear function assigns the number Ej. Now you see that the matrix consists of the row matrix, namely since D1 continuous on E that is Fx so that completes the proof of it. Okay, so I think that's a place where we can stop. Thank you very much.